So now, in this video, in this course, we'll talk about the inverse of a matrix. So in this section, we return to the matrix description, that is AX times B of a system of linear equations, and look for ways to use matrix algebra to solve the system. Before we actually start this, let's just start this section with this definition about what is this? The inverse of a matrix. And we know that actually in fundamental algebra, when we are solving this kind of equation, let's say 3x plus, let's say 6, 2x plus 6, that's equal to 0, right? How do you solve this? First, okay, we should just eliminate this 6 from left hand side. To do this one, I should subtract 6 from both sides, right? And here we have 2x, that's equal to 0, 0 minus 6 minus 6. Now I have to eliminate this 2. How can I actually eliminate this? We need to multiply this 2 by its multiplicative inverse so that we will have only identity element, that is 1. To do this one, what is the multiplicative inverse of 2? That is 1 over 2. That is 1 over 2 times 2x is equal to 1 over 2 times, here we have negative 6. So 1 over 2 times 2, that is 1. Here we have x, and here we have negative 3. And 1 times x in real number system, that is just x. And here we have minus 3. Okay. And also for matrix, if you're given the system like this, A, and here we have x, that's equal to B. And we know that that's a matrix, it's a vector, and also this is a vector, right? How can I multiply actually both sides of this equation by something so that here I will have identity matrix here, that is I, which is I times x will be equal to just, what is it, x. So that I can solve this system by applying a single operation on this, like this, in a similar way. So now to do this one, we have to introduce what we mean by multiplicative inverse of this matrix A. Okay, so if A is an n by n matrix, so you have to pay attention here, we are talking about a square matrix, now any, what is it, an arbitrary matrix. So A is an n by n matrix, and inverse of A is an m by n matrix, that is A prime, with the property that A times A prime equals I, and A prime times A equals I, where I is n by n identity matrix. If such an A, this one is supposed to exist, then A is called invertible. Okay, so that is the definition of a matrix. Now soon actually we will prove that every matrix, if it has inverse, it is unique. It doesn't have more than one inverses. That means that actually only one part is enough. But here that's the definition, so that A times A prime equals I, and A prime A equals I. If we can find such matrix A prime, then we say that A is invertible. That means that I can find it is inverse, and I can eliminate this A from here. All right, show that the following matrices are not invertible. That means that can I just find, let's say it is inverses O prime, so that O prime should be equal to I, and O prime and O should be equal to I, right? So we have two parts. Is it possible? If so, then it is invertible, otherwise it's not. To do this one, let's say the entries of this one is 2 by 2. How about O? Here we have 0, 0, 0, 0, right? And let's say the entries of this O prime, let's say this X, Y, Z, T. And on the right hand side, here we have 1, 0, 0, 1. But if we just multiply this one is 0 matrix, right? And here we will have 0 matrix, 0, 0, 0, 0. And on the right hand side, we have identity matrix, right? It is 0, 1 here. Actually, here, as you see, 0 is not equal to 1. So that means that these two matrices are not equal to each other. So that means that such matrix does not exist. We cannot find this. Even we don't have to check the second condition here, right? So we have proved that actually this matrix, zero matrix is not invertible. Are we recording? Yes. How about B? For B, in similar way, assume that this B prime is inverse, whose entries are, let's say, W, X, Y, Z. So by the definition, we know that B times B prime should be equal to I, and B prime times B should be equal to I. So let's just check the first part. Let's say this B times B prime should be equal to I. Actually, does it satisfy this condition or not? Or can we just find W, X, Y, Z, which actually satisfy this condition? So if we substitute here we have 3, 2, 9, 6, and here we have W, X, Y, Z. On the right hand side, here we have 1, 0, 0, 1. Right? So if you just multiply this, what we get here? Here we have 3 times W, 3W plus 2 times Y, 2 times Y. And multiply the first row by the second column, 3 times X. So here we have 3X plus 2 times Z, 2 times Z. And 9 times W, here we have 9 times W. And what is it? 6 times Y plus 6 times Y. And here we have 9 times X, here we have 9X, okay, 9X, and plus 6Z. On the right hand side, we have identity matrix 1, 0, 0, 1. Okay. So now we know that for two matrices to be equal to each other, they must have the same size. Okay, these are the things, they have the same size. We have no problem with that. And more than that, they are all corresponding entries must be equal to each other. So the first entry here, we have 3W plus 2Y is equal to 1. And here we have 9W plus 6Y. It should be equal to 0. Now, if you just solve this system, here we have 3W plus 2Y, that's equal to 1. Divide both sides by 2. 3W plus 2Y, that's equal to 0. On the left-hand side of these equations, we have the same expressions, right? 3W plus 2Y, 3W plus 2Y. But on the right-hand side, we have 1, and here we have 0. One expression at the same time, it cannot be equal to two different things, two different values, right? That means that this system has no solution. So even we don't have to check this, since it doesn't have solution, even the other part have solution. This one, we cannot find WX, right? That means that whatever you actually write a 2 by 2 matrix for B prime and multiply by B, it never produces identity matrix. So that means that this B, by the definition, it is not invertible. Okay, it's not invertible. Okay, just using the definition. All right, if A is an invertible matrix, then its inverse is unique. So now, actually, as you see here in the definition, we see that for a matrix to be invertible, it must satisfy two conditions, right? Number one is A times A prime should be equal to 0, or A prime times A should be equal to I, not 0, identity matrix. So now, since it is unique, then we need to check only one condition there. We don't have to check both. So if A is an invertible matrix, then its inverse is unique. In mathematics, a standard way, the general way, I mean, that's used by most people, to show that there is just one of something is to show that there cannot be more than one. So suppose that A has two inverses. Let's say it has two inverses. So the first one is, let's say A prime, and the second one is A double prime. So that means that here we have A prime is equal to A prime A, that's equal to I, because we are assuming that A prime is the inverse of A. And also we have another one. We are assuming that also this A double prime, another matrix. Also, we are saying that we have another inverse which satisfies this condition. A times A double prime is equal to A double prime times A. That's equal to I. Now I will show that actually this case is not possible. If it is possible, then A prime must be equal to this A double prime. That's our first approach. The second one is, so by the definition, that A times A prime, that's equal to identity matrix, and that's equal to A prime times A. And if we have A double prime is equal to I, and that's equal to A double prime, and that's equal to I. So here, if I just write this A prime, and I can write it as A prime identity matrix, nothing changed here. So here we have A prime. What is identity matrix? For identity matrix, I can just write this thing, that this one is equal to A times A prime, right? So instead of I, let me just write A times A double prime. By using the associative property of matrices, I can just write it as A prime, A, and here we have A double prime. And by A prime A, from here, what is A prime A? That's equal to I. So instead of this, I can just write I, and here we have A double prime, which is equal to A double prime. Now on the left-hand side, we have A prime. On the right-hand side, we have A double prime, which implies that A prime is equal to A double prime. So that means that if a matrix has an inverse, it cannot have more than one. That is unique. That's only one. It has only one, what is it? Inverse. Okay. So now let's just see how is it used to solve a system of linear equations. Okay. So this theorem 3.7, if A is an invertible n by n matrix, then the system of linear equations given by AX times B, AX equals B has unique solution, and the solution is X equals A inverse times B for any B in Rn. Okay. So number one, it says the invertible matrix is given, then the system of linear equations given by has unique solution for any B in Rn. That's our B, that's vector. So here we have two things actually. It has number one, we have to show that it has solution. Number two, we have to show that it is unique, right? Anyway, how do we do that actually? Here we are given the system AX is equal to B. And since it is invertible, it means that A has inverse. If you just multiply both sides by its inverse, here we will have A. Actually, soon I will denote it by, what is it? This notation, that is A inverse. So here we have AX, and here we have A inverse B. Okay. So A inverse I is A is just I. Here we have X, and here we have A inverse B. And that thing is equal to just X. That's equal to A inverse B. Okay. That is actually, what is it? The existent part. Actually, we have the solution. It has a solution. Now, to show that it is unique, it says it is unique, and we just assume that it has two different solutions. Anyway, here, let me just say that is existence, and second one is uniqueness. Okay. To show that, assume that we have two different solutions. Okay, we have another solution. Which one is, let's say, Y. Okay, so one solution is X, for example. Let's say another solution, let's say Y. So that means that when I substitute this Y into the equation, still it gives us B. Again, using the same procedure here, if we just multiply both sides by the inverse of A, here we have A inverse B. So A inverse A, that's equal to I times Y. The Y equals A inverse B. A inverse B is exactly the same thing, that's equal to X. So that means that X equals Y, means the solution is unique, only one solution. All right. So now let's start with how we find or evaluate the inverse of a 2 by 2 matrix. All right, so it says that if A, that's a 2 by 2 matrix whose entries are A, B, C, D, then A is invertible if AB minus BC is not equal to 0, in which case A inverse equals 1 over AD minus BC times the matrix. Actually, here, as you see here, the whole thing, it is AD minus BC, it's just a scalar. And why we are adding this condition? Because here, it appears in the denominator here, right? If we have 0 here, we cannot divide any number by 0. And that's why we should add this condition here. If AD minus BC equals 0, then A is not invertible. Okay. So you can prove this for general case, but here I'm just going to show you how we are evaluating this with a simple example. Find the inverses of the following matrices. Now I assume that we don't have the formula. Now you will see that our answer will be exactly the same actually with this formula. Okay, the second example, I'll just solve this by using the formula. So assume that I have to find the inverse of this matrix A, right? To do this one, I assume that, let's say, its inverse is this, whose entries are, let's say, X, Y, Z, W. Actually, I should write W, X, Y, Z. That's much better in alphabetical order. So here we have W, X, okay, Y, Z. Right. So since we are assuming that it is the inverse of this matrix, when we multiply them together, right? A inverse, that should be equal to 4, 7, 2, 6. And here we have W, X, Y, Z. It should be equal to identity matrix 1, 0, 0, 1, right? So now if you multiply them together, what we have here, 4 times W, 4W, 7 times Y, plus 7Y. And 4 times X, here we have 4X, 7 times Z, plus 7Z. And here we have second row, 2 times W, 2W, plus 6 times Y, 6Y. 2 times X, so here we have 2X plus 6 times Z, right? That is 6Z. On the right hand side, here we have identity matrix 1, 0, 0, 1. So actually, as you see here, we will form a system of equations. If we just take these two entries, we have 4W plus 7Y is equal to 1. And here we have 2W plus 6Y is equal to 0. I can solve this by substitution methods. You can other method, but it's just simple equation. So from here, W is equal to minus 3Y, right, from the second one. And substitute here, 4 times minus 3Y plus 7Y is equal to 1. So minus 12 plus 7, that's equal to minus 5. So Y is equal to minus 1 over 5. Okay. If Y equals this, from here, what is Z? Then in W. Then W is equal to minus 3, so it is 3 over 5. Okay, we got it. And the second one, here we have 4X. Let me just change here. 4X plus 7Z. On the right hand side, we have 0 because this corresponds to this entry, and this one, this entry. So here we have 2x plus 6z, that's equal to 1. Again, using the same method from here, x equals minus, no, can I use this here? No problem, I can just simplify this. So multiply the second one by 2, 4x plus 7z, that's equal to 0. 4x plus 12z, that's equal to 2. If you subtract the first equation from the second one, 4x minus 4x, 0, 12 minus 7, 5z equals 2. So z equals 2 over 5. And if z equals 4 over 5, what is x? X equals 1 minus 6 times z, that is 2 over 5 over 2, which is equal to, here we have 10, 5 minus 12 minus 7. So now I can just write the inverse of A, that is W. X, W is 2, I mean 3 over 5, WX. What is x? X is here, minus 7 over 10. And x, WX. What is x? Okay. Here we have minus 7 over 10. And here we have y. Y is minus 1 over 5. And z equals 2 over 5. Or as you see here, 10 is a common factor here. If I just take 10 out, 1 over 10, what do we have here? Here we have 6, and here we have minus 7, and here we have minus 2, and here we have 4, right? Now, if you just look at the formula, what we have in the formula, AD minus BC, right? That is AD minus BC. That means AD, that is 4 times 6, 4 times 6 minus 7 times 2, 7 times 2, 24 minus 14, that's equal to 10. That is our AD minus BC. And after that, we are just interchanging these two things, right? 4, 6 for 2 by 2. I will say here AD, now it becomes DA. And now here, these things, they're just changing their sign. So here we have minus 7, minus 2. So here we have minus 7, minus 2. I mean, even to get the general formula, we have to go through this system. Okay, now we will get the inverse of the matrix. In a similar way, by using the formula, you can evaluate this B. I will skip this question. So use the inverse of the coefficient matrix to solve the following systems of linear equations. All right. So to do this one first, let's solve A. We have to write this in matrix form. So this one, actually, I can just write it as 3, 7, 8, negative 5. And here we have x, y. Let me just write like this, x and y. And here we have 29 and 30. Right? So now here we have A times x. On the right-hand side, we have B. And we know that the solution is, what is it? A inverse times B. So that gives us the solution. So first, I need to find the inverse. So first, what is A inverse? That's equal to, here we have 1 over AD minus BC, 3 times negative 5. It is negative 15, minus 7 times 8, that is 56. Now, how about here? I have to interchange these two things. Here we have minus 5, and here we have 3, and change their sign. So here we have minus 7, minus 8. So which is equal to 1 over 15, 56, minus 1 over 71. So here we have minus 5, minus 7, minus 8, 3. Actually, we have a lot of minuses, so that's just equal to 1 over 71, and here we have 5, 7, 8 minus 3. Right? That is the inverse of A. So now, second step, I should actually evaluate this thing. So here we have okay. The second one, what is x? X equals A inverse times B. A inverse, we have just calculated here. That's equal to 1 over 71. And here we have 5, 7, 8 minus 3. On purpose, I'm just keeping the 71 out. I can actually bring this inside a bit later after we multiply this matrix by B. What is B? B is 29 and 30, which is equal to 1 over 71. And here we have 2 by 2 matrix. So we should multiply 5, right? 5 by 29 and 7 by 39. 5 times 29 plus 7 times 30. That's equal to 355. Second one is 8 times 29 minus 3 times 30. That's equal to 142. And 355 is divided by 71. Oh, it's divisible. So equals, if you divide this number by 71, that's equal to 5. And 142 is divided by 71, that's equal to 2. So dot, the solution of the system, which is x and y, that is, what is it? 5 and 2. All right, in a similar way, we can solve B, and also I'll skip this B. We can practice in problem solving session. So properties of invertible matrices. If A is an invertible matrix, okay, we mean now what we mean by invertible. We can find such matrix A prime where A times A prime that's equal to I, right? It says that then A inverse is invertible and its inverse is A. All right. So it's saying that it's actually can just also keep it in mind like -1 times -1 is just equal to A. Yeah, this is how we remember this. But actually proving this stuff is here to show that A inverse is invertible, we must argue that there's a matrix X such that A inverse X equals I, that's equal to X times A inverse. Right. First, A is invertible matrix. Then A inverse is invertible. First part is saying that if A is invertible, it's given. That means that I can find such matrix that A times, let's say, B, and that's equal to B times A, that's equal to I. Such matrix exists, right? And we know that, so since invertible, and we know that it's inverse, that B must be A inverse. That's how we denote it, right? Okay, that's invertible. Then A inverse, that's equal to A. How do you prove that? To show that thing, let's say A inverse, and here we have B, and that's equal to I, and that's equal to B times A inverse. So I have to show that actually A inverse, actually this B is the inverse of A inverse, right? And we know that here B equals A inverse, right? And every matrix has a unique inverse. That means that this A inverse here, that is B, its inverse must be, what is it? A, right? So from here, what is it? Since it has unique, and if I substitute here A, for example, let's say A, right? Actually, it satisfies this equation. Here we have A inverse from here, right, from the first equation. And also we know that every matrix has a unique inverse. That means that this A is the inverse of that thing. I'm not using actually A inverse, you may get confused. A is the inverse of that thing. So how do you write this? Then that thing's inverse is A. It's a little bit tricky thing, but if you just write it down and step by step, you understand what we mean here. All right, how about part B? Part B, it says that if A is an invertible matrix and C is a non-zero scalar, then CA is an invertible matrix and CA inverse, that's equal to, what is it? 1 over C times A inverse. All right, how do you prove this? All right, let me just write here. Part B is saying that CA inverse, right, that's equal to 1 over C times A inverse. Okay. So now I need to find actually this CA inverse, let's say times B is equal to I. That means that B is, what is it, times that thing is equal to this. And from here, what is this thing? Is equal to, I need to find such thing that when I multiply by B, it should be equal to I, right? And I need to show that this C times A minus 1 is equal to that thing, right? To do this one, if I suppose that 1 over C times A inverse, then what must be the value of B? This B must be, what is it? The, okay, now let me just do it in the other way. Okay. So assume that CA, oh, C is big here. Okay. If we have C times A, we have one matrix, all right? And it is inverse is, we know that C times A, which could be just, you know this by this. And that's equal to I, right? And I have to show that that thing, right, C times A inverse, that's equal to I. So from here, if I just multiply both sides by 1 over C, I will have here 1 over C times CA. And here we have CA inverse. Here we have 1 over C times I. Now this 1 over C times C is just a real number. They cancel each other. After that, I will multiply both sides by A inverse. So here we have A inverse A. And here we have CA inverse. Here we have A inverse 1 over C I. So A inverse A, that's equal to I. So here we have C A inverse, that's equal to, if you just simplify, it's just a constant number, take this out. So here we have 1 over C, and A inverse times I, that's equal to A inverse. So that's the proof of part B. And how about C? It says that if A and B are invertible matrices of the same size, then AB is also invertible, and AB inverse is equal to B inverse A inverse. Actually, I can just prove this in a similar way. After that, I'll finish the class. And here, they're saying that AB inverse is equal to B inverse A inverse. Okay. So again, here, as I say here, that is, let's say AB, right? That is one matrix times, and it is inverse, right? That's equal to I. Right. And how can I have that thing alone on the left-hand side? To do this, I need to eliminate this thing, right? So to do this one, first I multiply both sides by A inverse A inverse, and here we have A times B, and here we have, can I just multiply at the same time by like this? B inverse, A inverse. So here we have A, B, and here we have A, B inverse. On the right hand side, since I multiplied here by B inverse, A inverse, also I should multiply the left hand side by this expression, and by these matrices, here we have I. And A inverse A, that's equal to I. I times B, that's equal to B. And after that, B inverse times B, that's equal to I. So what is left here? Here we have AB inverse. And how about on the right hand side? We have just I here, right? And here we have B inverse and A inverse. Okay. All right, so in similar way, here we have if A is an invertible matrix, then A transpose is invertible, and it's just equal to A transpose. Inverse equals A inverse transpose. That's also interesting. First, if you just transpose and find it is inverse, or first find its inverse and transpose, we get the same result. And if A is an invertible matrix, then AN is invertible for all non-negative integers, N and A to the power of N inverse equals A inverse to the power of N. And D and A, you may just try and prove it, okay? So that's a general case, and from here we will continue on Friday. That is enough for today, guys. Thank you very much. See you on Friday. Bye-bye.